Hello everyone, and thanks for watching Edupedia World videos. In this video, we'll complete the unit of probability by studying the concept of Bernoulli Trials and binomial distribution. So in the previous video, we talked about random variables which are often created by doing what is called a random experiment. But we didn't focus on what a random experiment is in the video. And a random experiment, basically, as the name suggests, is an experiment in which the outcome is not determined beforehand. When you, let's say, make a collision between two balls, you pretty much know what's going to happen because you can write the equations of conservation of momentum and conservation of energy, and you know that if you hit a ball with a particular velocity at a particular angle, what the end result is going to be. So that's not a random experiment. That is the opposite of random experiment, what is called a deterministic experiment, in which you know what is going to happen, you just need to verify it. A random experiment would be flipping a coin or tossing a dice. In that you don't know beforehand what is going to happen, whether it's going to be heads or tails or what the number on the dice is going to be. And that is why it is called a random experiment. And we'll study a very specific type of random experiment, a subset of all random experiment, which is called a Bernoulli trial. Now, flipping a coin does qualify as a Bernoulli trial, but tossing a dice is not a Bernoulli trial. And a Bernoulli trial has a very specific property that the probabilities of what are called successes or failures are determined by a very simple equation, which is actually the binomial equation, hence the name binomial distribution. So let's first look at what the characteristics of a Bernoulli trial are. First of all, it has to be a random experiment. If it is a deterministic experiment, it cannot be a Bernoulli trial. So Bernoulli trial is basically a random experiment in which certain rules are followed. So the first rule is, this is just for the sake of completeness, this rule isn't really important. There should be a finite number of trials. A trial is basically one event in the experiment. And this is only there because theoretically you could continue an event for infinity and then these arguments wouldn't be valid. But in practical life, if you're conducting a Bernoulli trial, then there will be a finite number of trials. So this is not really that important. Then obviously the trials should be independent. So the probability of a success or failure on one event is not impacted by the probability of success or failure or another event. And that is actually the third rule, a subset of that, which is that there are only two outcomes. This is the first two are usually understood. This is one of the most important rules. There are only two outcomes. Only is important. And therefore they are referred to as the success S or failure F. So let's say we flip a coin and we define heads to be our success. We want there to be heads, and we define the event that X comes up on the coin to be a success. Then obviously there are only two outcomes. Either there will be heads or there will be tails. So it's a success or failure. If we toss a dice, then strictly it is not a Bernoulli trial because there are 6 possible outcomes. But however, let's say we want the number 4. So we say that the number 4 occurring on the dice would be a success, anything else would be a failure. Then it does become a Bernoulli trial because you have either the number 4 occurring or the number 4 not occurring. All the cases in which the number 4 does not occur, whether it's any other number, are treated the same as a failure. You can notice that there is no rule saying that the probability of success and failure need to be the same, 50-50. In a dice, if we say that the occurrence of a 4 would be a success, everything else would be a failure, the probability of success would be 1/6 and probability of failure would be 5/6. And fourth, this is also sort of redundant, the probability of success remains the same in each trial. So the first, second and fourth conditions are usually met in most experiments you will see. The third one is really the one that is important, an experiment in which you either have success or failure. Success could be defined any which way, is called a Bernoulli trial. So now let's say we conduct a Bernoulli trial 6 times and we would like to know the details of one success. So how can you have one success among 6 trials? Well, there are 6 ways. You can have the success and you can have 5 failures, or you can have a failure, success, and you can have 3 more. So I'll not write them. So there are a total of 6 ways you could have success, and so it can basically be written as 6 factorial by 1 factorial, 5 factorial. We already know this. Total ways of arranging them, 6 ways, and you could have 1 success, 1 factorial, 5 ways of arranging the failures. Similarly, if you wanted 2 successes and 4 failures, there would be a total of 6 factorial by 2 factorial, 4 factorial ways of doing that. So for this, we would like to develop a general formula for the number of successes you can have if you have a certain number of trials, and that ultimately comes out to be the binomial distribution. So for the sake of simplicity, first we'll not do 6 trials, we'll do simply 3 trials, and then we'll look at, we'll extrapolate it to 6 or any number of trials, which will be quite easy. So let's look at a Bernoulli trial where you have 3 events. So the total sample space. Now I would like you to not be confused between this S and the success. It's unfortunate that we use the same letter for both, but this is basically the sample space, which means the total possibilities of events. So if you have a Bernoulli trial 3 times, you could have 3 successes, you could have 3 failures, you could have 2 successes and a failure, SSF, SFS and FSS, and you could have 2 failures and a success. And these are the only possible options. 1, 2, 3, 4, 5, 6, 7, 8. So there are a total of 8 options, 8 possibilities in the total sample space. Now what is the probability that x is equal to 0? X is our random variable, which is the number of successes we have. So what is the probability that the success does not occur even once? So that is only one case in which all 3 of them are a failure, right? Now one mistake which you might do in a hurry is you might take the probability to be 1 by 8, because this is one event out of 8 events. Now what is wrong with that? When you do that, you have implicitly assumed all 8 events are equally likely. When you do that, you have basically assumed that the probability of success is the same as the probability of failure, which may not need be true, right? In fact, we will assume that it is not true. So we will assume that the probability of success in any one case is p, small p, and the probability of failure in any one case is equal to q, which has to be 1 minus p, right? So in this case, the probability x is equal to 0. We get it when you have all 3 failures. So it is the probability that you have f, f and f, and that basically is the probability that you have f multiplied the probability that you have f multiplied by the probability that you have f, and that turns out to be q cubed. So if q is the probability of a failure in any one trial, then the probability that you have no success is q cubed. What is the probability that you have one success? In that case, you have these 3 options. Sorry, one success means the other 3. One success means you have these 3 options, right? So it is the probability of either SFF or FSF or FFS. Now the probability of this happening can obviously be written as P of SFF, since these are independent events, plus P of SFF plus P of FFS. There will be no P of SFF minus P of SFF intersection FSF, because these are independent events, right? So, and now each of them obviously we can write it as, the first one we can write it as P of S into P of F into P of F, because once again these are independent events. Notice how everything we've learned in the previous videos, we are using that at every step. So again, the other two also we can write this as like this. So what we'll get is basically 3p q squared. Similarly, px is equal to 2. That means you have 2 successes, is basically SSF, SFS and FSS, these 3, and they would come out to be p square q 3 times, so 3 p square q. And finally the probability that you have x is equal to 3, all 3 successes, is the probability that you have SSS, which is p of s into p of s into p of s, which is basically p cube. So these are the important terms: p cube, q cube, 3pq squared and 3p squared cube. And what does this remind us of? We can see a binomial cubical expression here. We know that p plus q whole cube is equal to p cube plus 3pq squared plus 3p squared q plus q cube. But we also know that p plus q is equal to 1. So which means basically what we get is the sum of these is equal to 1. Well, actually that is something we already knew, because the sum of the total probabilities has to be equal to 1, because we have covered every possible case. So this is where the name binomial distribution comes from, because this is basically a binomial expression. Now what would have happened if we had 6 trials instead of 3? So instead of SSS we would have SSS, SSS, and obviously we would have a greater number of events, not only 8 but a much greater number. Then we would have had basically P plus Q whole to the power 6, and we know what that is: P to the power 6 plus 6 P to the power 6 Q 5Q plus dot dot dot. We already know the binomial expansion. So this would be the probability we had 6 successes, this would be the probability we had 5 successes, and so on. And so at the end what we can do is we can all write this into a neat little formula, which is that the probability capital X is equal to small x. Capital X is the number of successes, which in this case is equal to small x. Small x could be 1, 2, 3 or 4. This basically comes out to be equal to NCX into P to the power X into Q to the power N minus X. Because if we have small x successes, then we have N minus X failures, so these are the two, and then we could have that in NCX different ways. Right. So this is basically the ultimate equation which we derive from the Bernoulli trials. The probability that you have this number of successes will be this. So let's say you have, let's just take one quick example. You have a dice and you have 10 dice and you throw it together, right? And let's say you define the success to be either 1 or 6, and failure is 2, 3, 4 or 5. In that case, what is the probability of success? It is 1 by 3. What is the probability of failure? It is 2 by 3. And let's say you do this event, you take 10 dice and you roll them, so we'll have 10 particular dice at the same time. The probability that the success will be 4 out of 10. That means the probability that out of 10 times throwing a dice, we'll have 4 events where you have either 1 or 6 as the value, will simply be 10C4 into 1 by 3 to the power 4 into 2 by 3 to the power 10 minus 4, which is 6. Right. So this is the formula from which you can get the probability that you have a certain number of successes. It depends on what that number of successes is, but it also depends on P and Q, which are the probabilities of success and failure. Now if you take an experiment of just flipping a coin, then P and Q will be half each, because it's equally probable that we'll have heads or tails. This completes probability. Thank you.